This is the screencast of section 5.4, example 3. We're going to look at the fundamental theorem of calculus when the variable is the lower limit of integration, not the upper limit of integration as we saw in previous examples. So here in A, y equals the antiderivative from x to 5, not 5 to x, and we want to find the derivative of that y. Now the fundamental theorem only works when the variable is the upper limit of integration and the constant is a lower limit of integration. So we need to reverse those, and if you remember with your antiderivative properties, we can reverse the order of integration as long as we make that the opposite then. So this can be restated as the opposite of the derivative of the antiderivative from 5 to x of 3t sine of t dt. So now I am going to use the fundamental theorem of calculus and plug x in for each of the t's. Now technically I'm multiplying by x, the derivative of x, but that's just 1, so there's my answer. Now part B doesn't have any constants. It has a variable both as the lower limit and as the upper limit of integration. So we need to separate this integral into two different pieces and put a constant in between. So it's like saying, alright, if I'm taking the derivative from x squared to 2x, I'm going to find this a in the middle of the two. So it's the derivative, or the antiderivative from x squared to a, and then from a to 2x, then I have that constant. So I said this is the antiderivative from 2x to a of our function plus the antiderivative from a to x squared. So in total it would be 2x to x squared as the original problem was written. But now the goal is to find dy dx, so therefore dy dx would equal the derivative of the first part plus the derivative of the second part. Now we're going to use the fundamental theorem, but remember the fundamental theorem has to have a constant as the lower limit and a variable as the upper limit, which is not the case in this first term here. So I'm going to switch just this first term and make it the opposite. And now I have both derivatives of antiderivatives that have a constant as the lower limit of integration and a variable as the upper limit of integration. So now I can use the fundamental theorem of calculus, and I'm going to put 2x in for the t in the exponent of the denominator here. But now I also need to multiply by the derivative of 2x, which is just 2. And then, of course, I'm going to do the same thing here. I'm going to plug in x squared in for that t and multiply by the derivative of x squared, which is 2x. And of course you can simplify that by putting, well, you have a common, you don't have a common denominator, but you can put 2 in the numerator and 2x in the numerator if you would like. Like this. Either one would be an acceptable answer. The now try problem number 19 is another situation where we're going to take the derivative of an antiderivative, but this antiderivative has a variable in both the lower limit and upper limit of integration. So I need to split that into two different pieces. So essentially I'm going to find the derivative of two different things. The antiderivative from x squared to a or b or whatever you want to say of cosine of 2t dt, plus another antiderivative from a then to x cubed, totaling x squared to x cubed of cosine of 2t dt. Well, I'm not ready to take the derivative of both of these pieces yet because I have the variable in my lower limit of integration for this first term, so I need to switch that and put a negative sign in front, so I'm taking the opposite according to my property. And now I can use the fundamental theorem of calculus to be able to plug in that upper limit of integration with the variable into t. But of course I have to multiply by the derivative of that variable, or variable expression, so that would be 2x. And then this one over here, x cubed, gets plugged in for t, and then I have to multiply by the derivative of x cubed, which is 3x squared. You can simplify and put the positive term in front if you would like, and your final answer would look something like that.